presented. We're going to compare the types of the network addresses and explain how to configure global unicast and link local on the interfaces. So remember, this thing's tailored towards Cisco and the Cisco environment. One of the reasons why we're moving towards IPv6 is because of the issues that came with the IPv4. So we know that we have a dotted decimal representation for IPv4. It's a 32-bit address. There was only so many addresses to begin with. I think it was 4 billion. Is that correct? We know that there's at least 7 billion people in the world. There's not enough to handle all the needs out there. So IPv6 is going to eliminate that problem because we're using a 128-bit address space. The development of IPv6 also included fixes for some of the limitations, like broadcast. We don't broadcast with IPv6. We don't have to deal with NAT, right? Whereas we have to with IPv4 because of the loss. There's not enough addresses. So with increasing internet population, IPv4 address space issues occur because of NAT. All the new IoT gear, we got TVs, we got cameras, we've got speakers, we've got garage doors, we got thermostats. What else? Printers, tablets, notebooks, desktops, gaming systems, all in one house. So we got a lot of addresses that are required. So from now until the near future, we're going to coexist. We're going to run a multi-protocol environment. We discussed this. So when I started out, we were already doing multi-protocol environments because if I had an Apple lab, they ran a protocol called Apple Talk for all those machines to negotiate with one another. And then the Novell that was on the network for a server environment ran IPX SPX. So we're going back to a multi-protocol environment because we have IPv4, IPv6. So we were once we had moved into just IPv4 and transitioned away from a multi-protocol environment where we were running IP, Apple Talk, IPXBX, DECnet. We had all these protocols on a network for communications. We went away from that. We didn't need it. All we had to have was IP because everything ran across the internet. Now we're transitioning back into a multi-protocol environment because we want to get rid of IPv4. So until we can cut fully over to IPv6, we run both. So there's various tools, different methods. So we can see the dual stack would be the preferred method that I would choose, which means I'm going to run both 4 and 6. And I'm going to convert once I got everything fully over. There are also tunneling and translation capabilities. So we can create a tunnel to send our IPv6 packets over an IPv4 network until we're ready to cut over to a public IPv6. We can use a NAT64 application that allows us to translate IPv6 to IPv4 and back and forth send. Again, my preferred method would be to run both protocols in the dual stack format and then transition. That way I don't have to deal with additional. So you're going to, either way, you're going to have to run dual stack. You're going to have to run IPv4 and IPv6, right? Now I'm adding in to the mix this tunneling and translation method if I don't want to just do dual stack everywhere and make it function. Anyway, there's 3 methods that we can do this. What does it look like? Here's the IPv6 address in its formatting. So instead of periods, we use colons. We know that each one of these 4 numbers is actually in hexadecimal format. So we have A, B, C, D, E, and F in addition to 0 through 9. Each one of these represents 4 bits. They're not, when you look at this 2, it's not a 8-bit scenario, right? That's 4 bits and that 1, 2 to represent that. We have 4 characters across the field here. So 2001 is actually 16 bits. So all 16 bits are separated by colons. When you have 8 times 16, it gives us 128 bits. So we're doing a hexadecimal IPv6 128-bit address. In everything that we do, there's always been a network and a host identifier. All right, so in IPv4, you guys have learned that the subnet mask defines what is the network and what is the host ID, correct? In IPv6, we use something called a prefix. So they're going to give you a slash and some number. So from left to right, so where the 2001 starts, going towards the 200, we would count whatever number they give us to identify what portion belongs to the network. So left going right, we would count, and that's going to identify the network portion. Typically, you'll see them do a /64, which means the first 4 hextets belong to the network. If that's true to form in this situation, in this example right here, you can see that this is 2 different networks, because 8 and 8 and 8 and 8 is 64, and you can see that 1111 is different than 0083. And because these things are different, that means that this would be 2 different networks. Everything past the 64 bits, or what you do when you do the slash, would belong to the host identifier, or the node. So that the actual PC's address would be 200 in this case. Now, is that really 200? No, because it's in hex. So don't get fooled by that. There's a lot bigger number than 200. All right? That's probably 16 to the third there. And then 2 times 16 to the third is a big number. Does that make sense? Because remember, we do 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, all the way to 2 to the 7 when we were doing the decimal and the binary and the IPv4. This is 16s because it's hex. So it's 16 to the 0, 16 to the 1, 16 to the 2, and then times the value. And we know F is 15. So just so you know, when you get to F, to get to 16, it's 10. 17 is 11. So what looks like 11 is actually 17. 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, 1, 8, 1, 9, 1A, 1B, 1C, 1D, 1E, 1F, 2, 0. So 2, 0 is not 20, it's 32. Y'all good? Everybody's good with conversion? Make sure you guys know how to flip back and forth. It'll make it easier for you guys. So everybody's good with a IPv6. It's going to look like this. You're going to find out that there's going to be like 3 IPv6 on every machine. It's great. We get to keep up with 3 things. First rule of thumb. We already learned this because I taught you all in advance, right? We can make this smaller so we type less by getting rid of leading zeros. So anywhere I start with a 0 or I have 4 zeros, I can drop all the leading zeros. And it makes a lot shorter address for typing. It's a whole lot nicer to type this no leading zeros versus the full address. And you can type either one. Doesn't matter. They'll both work. But the end result is this. Okay? Everybody's good. So you can lop off leading zeros. Now we also have a special situation where we can use a double colon. But now remember, you can only use it once. So if I did the double colon here, I can look down here, I can see, okay, I got 3 zeros. If I counted them all up, if I put double colon right here where I have these 4 zeros, I go 1, 2, 3, 4, 5, 6, 7 spaces. So I know I got 1 that's a 0, which is what we have here. Now you wouldn't want to do that because you have more 4-0 environments over here further down the list, right? So we want to put the double colon right there in front of the 200. And then I can count this up. 1, 2, 3, 4, 5. So I can tell, I know that there's got to be 8 total. So I'm missing 3 hextets of 0. If I'd use double colon in 2 spots, you wouldn't be able to identify it because it could be 3 and 1, or 2 and 2, or it could be 1 and 3. We don't know where the zeros are supposed to go. So that's why you're only allowed to use it once in the address. That make sense? Everybody's good with that? All right, so again, that's a whole lot smaller than the one we had previous with the leading zeros and all the extra zeros. So now you get into the different types. All right, so everybody knows about unicast. Unicast is the same whether we're using IPv6 or IPv4. Doesn't matter, it's going to stay the same. We're going to be machine to machine. Multicast is used to send a single IPv6 packet to multiple destinations, the same as in IPv4. So that also stays the same. Anycast is something new. So this is kind of cool. So we take an IPv6 unicast address and we assign it to multiple devices. All right? So think about this. If you had a web server all running the same web application that all had the same static contact or content, and they all reached back to one SQL server, you could take and put an anycast address on all, let's say you had 8, on 8 servers, and because the content's the same, whichever one received the request first is going to respond with the results. Kind of cool, huh? So you can see this anycast address is routed to the nearest device having the address. All of them are going to be communicating the same information. Unlike IPv4 and IPv6, it does not have broadcast, so we covered that. There is no broadcast in IPv6. The only new addition is this anycast that we now know we're assigning multiple devices a unicast address that's the same, and the nearest, quickest response gets to handle communications. As we discussed, we have a prefix and interface ID, so that's /64 or /48 or /96. Whatever it is that the network administrators come with and gives you is going to define which portion is the network or prefix and which portion is the interface ID or the device address. Just like in IPv4, we can't have duplicate device addresses unless it's an anycast, right? So we're going to have a prefix which defines the network number. It's going to be all represented in hex, and then we're going to have an interface ID. Those two pieces come together to make up the total IPv6 address. Everybody good with this? So there are multiple addresses, as I stated it earlier. We have a globally unique, or GUA address. So this is one that's given to you by an ISP that's routable. It's allowed on the internet. This would be what the Google web server is running for you guys to be able to connect to with IPv6. Again, they're internet routable. We have a link local address. So this is required on every IPv6 enabled device. It is used to communicate with other devices on the same local link or LAN. So off the interface of the router or local LAN, we would use this address, this link local, to communicate with other devices on the network. This is not routable. You can see other devices on the same local link, the LLAs, or link local address, are not routable. And then there's another one that they don't have listed here that we're going to get into too, called link local. All right, so there is this FC00 to FDFF IPv6 unique local addresses. These are similar to IPv4 private. So when you guys see FC00 through FDFF, you can see that they're giving you the prefix of /7. So if they give you a /7, which bits are actually in play here? So it's just the FD portion, so I don't know why they have the 00FF stuff in there. That doesn't make a whole lot of sense. I'll look at this RFC and see if that is accurate. So the unique local addresses are used for local addresses within the site between limited number of sites. They're used for devices that will never need to access another network or to go out onto the global internet. They're not globally routed or translated to local IPv6 addresses. So many sites use private nature to attempt to secure or hide the network. This was not the original intent. So currently, when this presentation was developed, as far as Cisco knows, the global routing prefix was limited to the first 3 bits of your 128-bit address. They're doing a /3. So all the numbers that they're handing out. So we remember each one of these digits is actually 4 bits. So there's 12 in total in use. 2 to the 12 is a lot of networks. How many networks is 2 to the 12?
144. Right?
It's 12 times 12.
Oh.
2 to the 12. Doing math tables, multiplication. She'd have won that one. 12, 12.
Yeah.
How much? 4,096. 8 to 6. 5, 12, 10, 20. Yes, I agree with that. 4,096 networks. I would imagine that they probably have moved beyond that a little bit, but who knows. So these GUAs come from and are tied to the internet. These are public addresses, and they're handed to you by the ISP. All right. So currently, they say 1/8 of the total IPv6 space is being handed out. So maybe they're slow rolling companies on. The global routing prefix is a prefix or network portion assigned to you by the ISP, AT&T, Verizon, whoever it is. The subnet ID field is the area between the global routing prefix and the interface ID. It is used by an organization to identify subnets. We discussed this, so the prefix we're allowed to change. The ISP is going to give you some value. And so if there's 4,096 and they're only using those prefixes at the global level right now, my guess is that those 4,096 addresses are only being handed to ISPs. So globally, all over the world, there's only up to 4,000 entities that matter. Does that make sense? That are handing out addresses. They're taking those, whatever they've been assigned, out of the 4,000. Since it's a lot bigger number, and then they're adding to it to assign to an end user. You guys with me? So like at the front end, if somebody had, let's say AT&T had 200 as the front part of that address, they could take and assign you 2001. They could assign somebody else 2001A, :A. And they'd say you're going to use a /16 or you're going to use a /48 or they have a whole lot more space to work with because they have that one that's, we know, a whole lot more addresses because it's 128-bit space. So the IPv6 interface ID is equivalent to the host portion of the IPv4. We've discussed that. So packets, how do we get this LLA? So with a source destination LAA, we can't route, we can't go beyond from one network to another. Every IPv6 enabled network interface must have an LLA. If it doesn't, it has to be if it's not manually set, it will generate one. So you can see that they all start, your linked local addresses on interfaces on the routers and on the PCs will all start FE80. We can hand these, we can manually put these on, or we can have them auto kind of calculate. See, it will automatically create one if you don't assign it because it's required. Manually configure, or we let it generate. Preferred method is going to be to put it in because we don't want it automatically generating something that's useless to us. All right, so here's your first new command, which I think you've seen already because I've done it in the classroom. But if you wanted to set an IPv6 address on your router interface, we go to the actual physical interface. We do IPv6 address. We punch in the hexadecimal address with a prefix. So you guys can see 2001 DB8 ACAD1 is the network, and then the actual device address is 1. And then there's 3 leading zeros because they did a colon. You guys should be able to see that now that we've discussed IPv6 address. So the /64 says from here to this way, if we count, 64 bits over is the network portion from left to right. Is everybody good with that? Don't forget to no shutdown. While you're on this interface, you might as well go ahead and assign the IPv4 address. So that's IP address and then the address. So it's going to have both. All right. They just left it off the screen. So the same command, we go to the interface and we put the IP address. I think there's some confusion between switch and routers. On every router interface, we put IPv4 and 6 addresses. Every router interface is a different network, has to be, because they overlap, it's a problem. On a switch, we can put an IP address, but the switch IP address goes on the VLAN, right? As far as semester 1, where we're at right now, I think on the switch, they're only going to require you to put IPv4. Okay. When we get into the next semester and we get more advanced, I'm going to make sure that you know how to put IPv6 on a switch. The switch does not route IP. It does not look at IP unless it's a layer 3. All the switches in the lab environment, those, what's the switch number? They're the silver 3700s, I think, 3750s. You Google Catalyst 3750, just so you guys know. Those do all have the latest 15 iOS, because I went and dug it up, put it on there. They all do support layer 3, so they have some routing functionality. That's not, as far as you're concerned, that doesn't exist, but it does. And so those can actually run IP4 and 6 addresses inside the lab environment. Those are enterprise class layer 3, they're multi-layer switches. So they're a little bit more than the norm, which means I can move stuff from one VLAN to another at the switch. I don't have to go to the router and have it do it and send it back. All right, so everybody good with the signing the IPv6 address? So this is the GUA. This is not the link local. This is your GUA address. They will provide these to you on the lab sheets. So not only do we have to put the IPv6 and IPv4 on the router, but we also have to put it on the PC. So within the same properties on the network card of your actual physical PC, or within Packet Tracer, you should have an IP configuration section for both 4 and 6. So you can see here we're setting up IPv6 with the prefix, because we don't use a subnet mask with IPv6. And the gateway address points to what you saw on the previous slide. Oops, wrong way. The previous slide on the interface. So you can see whatever interface you're connected to on the router, the IP address you put on the router is what goes into the gateway field. So if I'm working on the machine that's on :2 network, and I put :1 as a gateway, it's not going to work. The gateway has to be the interface that I'm connected to through the switches. Will a PC function with just the prefix and IPv6 address? Yeah, in the local environment on the switch, all these machines can talk to one another without having a gateway. What it won't do is it won't leave this room and go to the next network down the hall, and it won't go onto the internet without the gateway. If I have an IP, a subnet mask, and a gateway, and I have an IPv6, a prefix, and a gateway, I can go anywhere I want in the world as long as I know the number. Did y'all know that? So if I knew that Google's address was whatever the IPv6 address is, I could type that into a browser and get there. I can't use the name without the DNS. So you can see they left this blank. So in the real world, we know that, hey, if I'm going to be typing www.google.com and trying to get there with the IP address, then I've got to have DNS configured. All right, so here's your second command that you need to add to your notes. The link local, you can see that they're going to give you this in the lab and on your packet tracer. So in addition, earlier on the slide when you guys were typing the IPv6 address, we didn't have to leave. We could have done IPv6 address space FE80::1:1 space link dash local enter. And then we could have done the no shutdown. They just broke it into 2 slides. We're going to do both the link local and the GUA on the same interface at the same time, so you don't have to do it twice. You guys with me? So this is the manual add of the link local. Has everybody got it written down, typed? Silence means yes. All right, so what if we wanted to dynamically assign the addresses? So when you guys get into the real world, you're not going to want to type 250, 1,000 different addresses on all these different devices on a network. It doesn't take long to go from 2 devices to 80. All right. If you got 10 people and they each have 2 devices, you're already at 20. Right? Tablet, notebook and watch, whatever those devices are. It doesn't take long to get to an 80 device network anymore. So how do we do these dynamically? So in the Cisco world, if we're using the ICMP version 6 message formats, we can request from the router or the Cisco device with a router solicitation message, hey, I'm on the network, I'm running IPv6, and I need an address. Right? The router will respond with an RA that's sent out by the routers to inform hosts on how to obtain their GUA address. We're going to say, okay, hey, this is where you're going to go get it. Here's your prefix, here's your gateway, here's your so all these things that we're manually typing in right now in semester 1, we want to learn how to do this dynamically so we don't have to type them in every device. I don't even type them in locations where I have something that doesn't want to change. So for example, a printer. That printer, copier, scanner, those things, I want them to get a fixed address that doesn't change. So just so you guys know, through dynamic methods, I can tell the device that's handing out the addresses or assigning these addresses, hey, look, there's a copier and it has this MAC address. All right, when you get a request from it, I want it to have this information. So it'll always get that address till that machine is gone. And then we would replace the MAC address inside of the what I call a reservation, so that the new device would get that address going forward. Does that make sense? And that way you don't have to physically put it in on there. So things like phones, if you want them to get a specific address, you take the MAC so we can plug it in and we can say, hey, here's your address. And it will never change. It'll always be, but we're handing it to it. We don't have to go configure it. So you're getting rid of a lot of typing by being able to do that. So we're going to want to know how to do dynamic host configuration protocol, both version 4 and 6, and then how to assign addresses. Linux can do it. Windows Server can do it. There are other third-party tools out there that can do it. Some of our routers and devices can do it. Small environment, the router's fine, but I prefer to use the Windows Server because I can take and add more than one Windows Server all run in DHCP, and I can break the pools up. That way if one fails, I still have 2 handed out. Anyway. So Slack is another method to allow us to configure an address along with the DHCP server. So you can see we configure a GUA without the DHCP v6 services. They obtain the information from the ICMP router and advertisement. Okay. The prefix is provided to it, and they use this EUI64. So that's something you guys can look up. EUI64. How does it work? We're in the network environment. So it's going to randomly generate this client information. You're going to know that EUI64 is in play because when you see one, after the solicitation occurs and our machine gets it, it's going to look like this. Y'all have seen a MAC address before, right? Well, they take and they throw portions of the MAC address into the device ID. All right, so they took a 48-bit address. We only needed to fill it up to 64, so they added it in on my 64-bit address. So you can see they put an E after the initial F, and then they did an FFFE in the middle, and then boom, we have a device ID. And so if you look at your MAC address with ipconfig all, and then you look at your IPv6 address that's assigned, and there's a big portion of the MAC address inside the address, you guys now know, hey, that thing was dynamically created with EUI64. Y'all with me? Y'all see it, right? So here's a FE80. You can see that they have the IPv6 address. So depending on the operating system, they can use a randomly generated. This, I imagine, if you guys do an ipconfig/all, is not EUI64. The MAC address is maybe in here, maybe not. So beginning with Vista, Windows uses randomly generated ID instead of creating EUI64. So this one probably does not have the MAC address in here, but you can see the link local and the IPv6 have been manually generated or randomly generated by Windows itself. To ensure uniqueness, so this is something IPv4 does not have. If you guys put a computer on the network and it comes up and it says, hey, we have IP duplication, duplicate IP exists, something to that effect, whether it's on the router or the device, it's a warning. It's letting you know that some other device on the network has your address and you're going to be semi-functional, okay? Because two people have the same address, which is not allowed. IPv4 will not fix it. There's something called DAD, duplicate address detection inside IPv6. So if it detects it, it's going to go through and repair. It's going to say, we're not going to use that. We're going to find a different one. It's going to randomly generate a new one. Okay? So it does an ART to see if that address is out there. And as long as there's no reply, we're going to continue to use that address. But if we do get a response, we're like, oh, problem. Let's try again. It's going to go back through the random process. IPv4 will not do that. It will just say, hey, you need to fix this. There's a duplicate somewhere. And I can guarantee you, like in this room, we got, what, 28 machines? Something like that. If we started looking for where the duplicate was in here, it's always the last one or two machines that you get to find the one that's causing the problem. So you have to touch each one to figure out who's got the address that you're trying to say, hey, don't do this. When you go through the machines, it's always the last one or two that you get to that have that problem. All right, so this figure shows the LLE dynamically created using the FE80::/10 prefix and the interface ID using the EUI64-bit process. Again, we go look at the MAC address on this adapter. I can guarantee a big chunk of this part right here has been pulled from the MAC address down in. These commands are important, so you put these in your book. If you haven't been using them, you should. So show interface gigabit Ethernet, and it may be 0/0, it may be 0/1, it might be 0/0/0. You guys are going to know what that is because you've plugged into it. You know if you have slots or if it's just a card that's out there. We can do show interfaces enter, it'll show you all the different ones, so that will identify how you're going to do this. We're just keying in on a specific one because that's the one we're plugged into that we configured, right? All right, so these are important notes. Like all the people that don't show up, they get to miss this. So when we do this show interface gigabit 0/0/0, you get a lot of vital information. So for one, if I see up, so gigabit is up and the line protocol is up, this is good. That means both my IPv4, IPv6, and the interface itself are all fully functional. If you guys see gigabit Ethernet 0/0/0 is administratively down, that is bad. So what's that tell you? It's down administratively. So what does that mean? What did you forget? You forgot to do no shutdown. You did not turn the interface on. It is off. All right, non-functional. Everybody with me? So you can see Ethernet is down, but line protocol is up. That's not good. So if it doesn't say administratively down, what does that mean? So if it was down and line protocol's up, what y'all think it would mean? Something's not configured correctly. For sure, I agree with that. So what would not be configured correctly? So this right here is referring to the physical interface, and it's not up. In my mind, that means that it's not plugged in at the other end of the switch. The cable between whatever I'm plugged into is not good, or I use the wrong type of cable, or just not plugged up at all. But I did configure the IP, so the protocol up is IP, just so you guys know. So if I saw up and down on the protocol, that tells me that you guys didn't do IP correctly. So that one line right there gives you a lot of useful information in troubleshooting your problem. So we now know if we see administratively down, oops, forgot to do no shutdown, that's easy fix, right? If I see, hey, it's down, better go check the cable, make sure I got a light, make sure I'm using the right cable. If I see line protocol is down, I better check my IP address and I'm probably not doing it right. Make sense? So you get the MAC address, you get whether the interface is online, they cut some of this other part, they did the brief. So I don't know if you figured it out yet or not, but show IP is IPv4, show IPv6 is IPv6, IP is IPv4, IPv6 is IPv6. IPv4 routing is on by default. There's a command IP routing. If you look inside your show run, you'll see that it's already there. We've built these routers when they leave to go ahead and route IPv4. IPv6 is non-functional until you enable it. Does anybody remember how do you enable it? How do you turn IPv6 routing on? So they're showing you that you can look at the addresses as you configure them. Does anybody remember? IPv6 space unicast dash routing has to be run. IPv6 space unicast dash routing has to be typed in global config prompt because it's off by default. It'll enable it. It shows you right here. So just so you guys know, they're going to give you more of these addresses, like 223, 224 in IPv4 world or multicast. When we get into anything FF, and so just right out the gate, FF02 is a special group. If I'm trying to send a packet to a group, any of the other IPv6 addresses listening on this link will respond. So all nodes in the group that are using FF02. This right here, FF02::2 is a different one, and this is for all my routers that are participating in the group so they can communicate. When we get into RIP, it'll have its own IPv6 multicast and IPv4 multicast addresses that it uses. So RIP's one of the dynamic routing protocols that we're going to get into next semester. OSPF is another one. It'll have its own addresses. You need to know these and memorize these because they will show up on the CCNA. It's not like I'm being mean and I want you guys to memorize these. I'm telling you that this will show up on the CCNA, on one of y'all's CCNA tests. And it may not be this one, it may be one of the other multicast addresses, but they will show up and they'll expect you to know that that's multicast for whatever. You've already seen the questions that show up on the NetAcad test. Those things are close to what you're going to see on the CCNA, except you already know the level of difficulty of the questions that they have. You haven't pre-looked them up, right? When you get to the CCNA, they've enhanced or made them even tougher. So they're not trying to trick you. They just want to make sure that you know this because we don't want to just send anybody out, put them on a network that leads to bad things. Okay. We're in charge of the accounting systems that run all the payroll for organizations. They used to be separated off, right? It's all done across IT now. We're in charge of all the things that handle all the transactions. So for example, like the business office, all of their stuff that handles all the stuff that moves it in and out of your SOAR accounts, it's all handled by IT, right? They have people there, but it's in the end, it's all IT. When you guys register for classes here, all handled by IT. Can you think of anything that's not tied to the computer? That you physically have to go somewhere and do it? You can't do it with an app? So you see where I'm going with this. Like, we really, really have to know what we're doing because the better at it we are, the more money we can make. That's the end goal. Because you'll get asked this question at least once, if not multiple times in your life. Well, why should I pay you more than this other guy or girl? I got 30 years on them. Here's my first answer. Worth more experience. Oh, well, they said that they could, you want somebody that just read a book to do your network? Great. Good luck. Anyway, so my point is, the more that you guys can learn this, the better you understand it, the more you can turn that into experience, the more money you'll be able to make. You're already at an advantage because when you leave, you're going to get probably double what anybody else with a degree is going to get at a bachelor's level. See it all the time. So I've seen students that grasp most of the content making very big numbers, and I see folks that really, really get it, they make way more money. So it just kind of depends on where you go, what city you go to, what market you get into, but knowing this is important. A solicited node multicast address similar to all node multicast. It's mapped to a special Ethernet. This NIC can filter the frame by examining the destination MAC address without sending it to the IPv6 process. So you can see that it's filtering out here, and these guys are going, hey, it's not for me, it's not for me. They're going to have you guys go through that in the lab. So we can have something called a subnet within IPv6, because remember, they're going to give you this prefix. They're only using the first 12 bits. All right, but the ISP may assign you 48, right? All the rest of that 128-bit address is ours, recommended up to 64. So if I take 16 bits to generate networks, and I'm in charge of all the networks, and I only have like 4, it's not real hard to create an ID, right? 2 to the 16 is what? You guys should know this one already. 65,000 plus networks that are all global that you can generate from right there. All the rest of this is host addresses. 2 to the 64 host addresses on my 64,000 or 65,000 networks. If you're one entity, you think you're going to outgrow that? Probably not. It's insane. Okay, you guys with me? So what they're going to give you some number up to the first 48 bits. So we know that means the first 3 values that they separated with colons, right? Because each one's 16. And then we're reserving the 4th one for what we create. So I could use 0000, that's an ID. I could do 0001, that's an ID. I could do 0002, that's an ID. Each one would be a different network because it's changed. If I wanted to write 10, I would write A. Okay. You guys with me? If I wanted to write 16, I would write. Nope. Zero, zero, 1, 0. Yes. The 16 is a 1 with a 1 there, 16. And then we fill over to 16 to the 0. F is 15. So to go up, we move the 1 over, start rolling. Trick questions. So you guys good with that? So if I tell you to do the 15th subnet, it's F. Right? I think we count up. Is that, do we have 15 bits or 16? So 0 through 9 is 10. A, B, C, D, E, F, 6. So that would actually be the 17 if we count 0. Right?
Right. Yeah.
16. It would be the 16.
I mean, I did that.
So 0 through 15 is 6. F would be the 16th subnet. So the 17th subnet would be 10, so on and so forth. Whole lot of bit combinations there though, because we got 4 values and 16 different characters, and we can flip them all around into different packs. 65,000 to be correct. So it looks like this. So each one of those things can go on a different router interface. So in semester 1, we're concerned with, hey, a network goes on a router interface. If I want another network, I create another network interface, so on and so forth. We're going to figure out that I actually could have one interface and it could have like 15 networks on it if I wanted to, because we're going to learn about something called VLAN and sub-interfaces. A actual interface can have more than one address on different networks, just so you know. So on mine, I physically do all kinds of different addresses so that when I go somewhere and I'm configuring a different piece of equipment, I don't have to go in there and change my adapter. Because like I know if I go to plug to a Comcast box, it's going to have a 10110 by default. If I go plug into a Netgear, it's going to have like a 192.168.0. If I go to Linksys, it's going to have 192.168.1. Does that make sense? Well, I can put different addresses on my interface. You're allowed to do that. All right, so you guys good with this? So all that stuff in red is a different, what we call network that we're creating and we're in control of. So you would keep track of that. So I can say, okay, 00 is the Forest County Hall building, 01 is the Sienna Hall, 02 is Forest County Hall, 03 is the admin building, 04, so on and so forth. 65,000. Come on, lost my touch. Machine died. Oh, there it is. All right, so 5 subnets. 1, 2, 3, 4, 5. Actually, I got 6 over here. Oh, 1. That's right. You got 1, 2, 3, 4, and then this one. So every interface off the router, this one counts as 1 because they're talking to one another. Is a different subnet, so we would pull a different number over here, and you can see that they've done that 1, 2, 4, 5, and 3 from the pool over there. So here's an example of each router interface and you assigning the address. You guys now know not only are we going to do this, you guys are going to also assign the link local, unless we're going to let it randomly generate. And that's all of IPv6. All right, because we're a little bit behind, we were going to do 11, 12,